Next, we have another one of our entrepreneurs. She's only in the university a handful of years, but she's already come up with a wonderful technology to try to address one of the most important problems that we have, and that is biofouling. Please all, let's welcome Meital Reches. Please.
I'm going to present to you today a technology that was established in my lab at the Hebrew University at the Institute of Chemistry. And based on this technology, I co-founded the company NanoAF. And the technology tried to fight bacteria and try to actually solve a problem which is much more general, and that is the problem of biofouling. So biofouling is the undesirable attachment of organism to the surface. It's initiated by adhesion of biomolecule. So if I'll touch this chair in the room, I'm going to transfer a bunch of molecules from my hand to this chair. So many fats and proteins and polysaccharides. And now these biomolecules will be the glue for other things in the room. So I hope you're all healthy today. So I hope the bacteria are friendly and they just sit on this chair. But in hospitals, that's actually a problem because we're not talking about friendly bacteria, we're talking about pathogenic bacteria, so harmful bacteria that will now adhere to the chair and will talk with each other and form this social network that will allow them to become super bugs, right? So bugs that are resistant to antibiotics, bugs that are actually cause the problem of hospital-acquired infection. And these bacteria, they're not just causing health problems, they're also a glue for other organisms. So let's say if we're in the ocean, if we have a ship in the ocean, now these bacteria will be the glue for other organisms, so mussels and barnacles. And so this is a problem in many areas. So hospital-acquired infection, this is one. This ship that you see here, which has lots of organism on it, is now heavier and consume more fuel, so you actually need to apply more energy to transfer whatever you wanted on this ship. And the last area is water distillation facilities. So in water distillation facility, you want to flow water, and with water you also flow organism, which now will clog the system, and so you need to apply more energy to pass the same amount of water in the distillation facility. So just to give you some number, so 6,000 people die each year in Israel from hospital-acquired infection. That means they got hospitalized for something else, so let's say a hip replacement, and got infected with certain bacteria and died from the infection. In the States, the number is 100,000 people each year. For marine fouling, this is an economic problem. We talk about $150 billion a year. That's the annual cost for the marine industry to deal with marine fouling. And actually, this is not marine and health. It also relates to any surrounding that has humidity or water. So if we have an implant in our body, our food, so food preparation and packaging, our food can be contaminated. Our home appliance, my washing machine has a lot of mold in it. So every environment that involves a little bit of water. And so this is a major problem, and actually many people try, both in the industry and academia, try to solve this problem, but there is no ideal solution. So when I was a postdoc at Harvard a few years ago, I went to this lecture at the Boston Science Museum, and they talked about silver particles and how silver particles will be the next antibiotics. And today, it is known that there are actually bacteria that are resistant to silver particles. So they can survive, as they survive different antibiotics, they can survive silver particles. And also, silver particles are toxic, so they are banned from use in the States today. So other solutions are not stable enough. I don't know if you know the name polyethylene glycol. That's a polymer that you take as a nutrition fibers. And the idea is that the fiber, they come in and they don't interact with anything in your body. And this is because they do not interact with any protein, any biomolecules, and this is why they're very good anti-fouling material. They prevent the first step of fouling and then prevent adhesion of any organism into it. The problem is that they tend to self-oxidize, so they're not stable enough. So there are other solutions that are just too restricted to certain surfaces, so you can just put them on, let's say, metals or put them on plastics. Some of them are just too complicated to apply, and some are just too expensive, so the industry do not want to adopt them. So my solution is peptide-based antifouling coating. And peptides are molecules made by amino acids, so natural biomolecules. These are the building blocks of a protein in a body. And they're not toxic, and they can self-assemble. So they can talk with each other, as Odette mentioned. They can talk. These are natural molecules, so they talk with each other like Lego building blocks and actually can build complicated structure. Another advantage is that they're stable. So we synthesize them in the lab, and we have this powder, and the powder is stable. You can store it in the refrigerator for years. And another aspect is that the synthesis is pretty easy and can be scaled up. There are companies in the US that can scale this process up into kilograms and tons. So here's the molecular design of the molecules. So this is a short peptide, only 3 amino acids long, and it contains 3 elements. We wanted to design a molecule that will adhere to anything, to this carpet, to the chairs, to the ceiling, any surface, any type of surface, will form a homogeneous coating, and the coating will be a non-stick surface, like this Teflon pan that you see on the screen. And so for the adhesion, we took an element from this creature that you see, or organism that you see here, marine mussels. So again, when I was a postdoc at Harvard, I heard a lecture talking about this organism and how they attach very well to different surfaces, right? You can see them in the sea, in the ocean, very high salt concentration, and they can attach very well to rocks, and they can actually attach to any surface. And they do that by having proteins that can stick to anything. And what's special about this protein is that they contain the amino acid dopa. So we decided dopa would be a good adhesion element. It will stick to anything. And then we wanted to have an element that will allow the molecule to talk with each other and self-assemble into a coating. And this is inspired by my work as a PhD student at Tel Aviv University, where I discovered that if you have aromatic amino acid, so amino acid that has this hexagon structure, if you have this in your peptide, the peptide will self-assemble in a certain way to mediate the self-assembly of highly ordered structure. So I chose to design, to have in a design aromatic amino acid. And now the last element is the antifouling element. And I taught, I just started my lab at the Hebrew University, and I taught a class, Introduction to Chemistry of Material. And I taught the students about different polymers, and one of the polymers was Teflon, which is a non-stick surface. And Teflon has unique properties, so it has a carbon-fluorine bond. And I decided I can incorporate this element, this fluorine atoms, into my molecule to have a non-stick surface, so to mimic the chemistry of Teflon into peptides. So the idea is that I'll have a very sticky molecule at one hand. It will self-assemble and form a non-stick surface at the other hand. So we synthesize the molecule in the lab. We have a powder. We can dissolve the powder in different solvent. And now we can dip a surface in the solvent, and the molecule will self-assemble to form the coating. And we can also do that by airbrush. So we can actually take an airbrush and spray the molecules onto the surface, and once the solvent evaporates, the molecule will self-assemble into this coating. Does it work? Yeah, it works. It prevents the adhesion of bacteria to the surface, so it reduces the amount of bacteria by 90%. It can stick to different surfaces, so it can stick to plastics, to metals, to glass, actually any surface we tried. And it also reduced the attachment of other organisms because it's a non-stick surface, so it prevents the first step of fouling. So it prevents the adhesion of biomolecules, and by that prevent the adhesion of bacteria, and it can also prevent the adhesion of fungi, yeast, and different other organisms. the next question was, is it stable enough? So I can tell you today, yes, it is stable. It's stable in seawater. So we actually tested that using the Mediterranean seawater. You can expose it to different pHs. So you can expose it to acidic solution and basic solution. You can expose it to high temperature, so up to 200 degrees. It has a good mechanical stability, so you can scratch it. It will not be scratched. And it's non-toxic. So based on this very good result, we established a company. The company calls NanoAF. There are 5 members beside me in the group. There is 1 microbiologist who just joined. The company is located at the Ankara campus of the Hebrew University. And just to give you an overview of what was the milestone in this process. So this idea actually started, as I said, when I started my lab. And to fund this idea and actually get it from the idea to actually having the molecule in hand, we had a seed money from the Hebrew University, so through the Nano Center, and then through the Israel government. So we had this pre-seed money. And once we had this proof of concept, we started talking with companies. And we are amazed by how the companies are actually interested in finding a solution and how there is no ideal solution to the problem. So we established a company, and we obtained a license, exclusive license from Yizum. And then we raised some funding, again, from the Ministry of Economic, and some more money from angels. We collaborated with Samsung as well, and actually started different collaboration with different companies. So this is now a global, I would say, different global organization, and mainly Dow Chemicals, Mekorot, so different companies in Israel and outside of Israel. I would say the main focus today of the company is water food, so Mekorot and Dow on water, and Tnuva, which is an Israeli company, on food. So I'll summarize here and just tell you we have a new solution to fight bacteria, a simple solution. You can just spray it on different surfaces, and the coating will prevent the adhesion of bacteria and other organisms. It can be useful in many areas. So it can be applied to implants, food preparation surfaces, water distillation facilities, any humid environment that suffer from the problem of fouling. We established this company, NanoAF, which is on the campus of the Hebrew University, and this is a very important connection between the university and the company that came out of it. And we are now in a fundraising mode. This is the stage of the company, and I hope you will come and talk to me more about this solution. Thank you.